Good morning, everyone. I hope you are doing all right and ready to learn some physics here. So, last week we started talking about work and energy. And remember, conservation of energy is one of the three main basic concepts we learn in this physics class. Other two were kinematics, dynamics, or laws of motion. So we did all those, right? Of course, the vocabularies or the definition, they are always there. So today we're going to be talking about one more energy. Remember last class we talked about kinetic energy, which comes from the, when any force, net force does a work, the velocity of object may change. When that happens, what happens? Kinetic energy changes because kinetic energy is half mass times velocity squared, right? So that is kinetic energy. So now we're going to introduce one more energy, which is potential energy. More specifically, it is gravitational potential energy. And after that, we're going to move to conservation of energy. So in this class, we're going to be mostly talking about two kinds of conservation principle, conservation of energy and conservation of momentum. So conservation of energy, one of the main concept, and it can be used to solve problems in wide varieties of problems. So it is very important topics, okay? So before we get into conservation, let's learn about gravitational potential energy. So energy basically comes from the, it is the, let's say when a force does work, energy transfer takes place, okay? So the amount of work done appears as energy. So kinetic energy, we said change in kinetic energy comes from the work done by net force or all possible forces. But if we isolate just one force, gravitational force, and we find work done by gravitational force, what do we get? We get what we call gravitational potential energy. Sometimes in short, it is also known as GPE. It is not GPS, it is GPE. It's energy, gravitational potential energy. Okay. So what is it then? It is simply the energy transfer that takes place when gravitational force is doing work, when we take account of work done by gravitational force only. Okay, so that's what it is. So we have to go back and recall this equation which we use to calculate work done by any force. So work done by any force is equal to the product of the force and displacement caused by that force and cosine of angle between that force and displacement, right? So that's how we read this equation. So now here what we are trying to do is trying to find work done by gravitational force. And gravitational force, when we are near the Earth's surface, it is always acting towards the center of gravity. So that means it's always vertically dampened. So for example, let's suppose when this bucket is being pulled by this tension force here on the rope, the gravitational force is acting there, right? Oh, my bad. I did not realize my microphone was way farther. Okay, sorry about that. So now my microphone is close to me. Hopefully it's gonna work better. So now what I'm doing is I'm using this formula to find the work done by this gravitational force that always acts vertically down. So for the gravitational force, I'm putting this subscript G for gravitational force. And of course, I can write that as a mg as well, which I'll do soon. And H is displacement. So this bucket is moving up. So that means our displacement is this here, H, the change in height in this case, because bucket is being pulled up, and cosine theta. So in this case, how do I find cosine theta? Just like in any situation, when there is a force, for example, force of gravity like this, and displacement like that, the angle between them, we can see after we draw them, it is 180 degree. So angle between them is 180 degree in this particular case, when this bucket is being pulled up, okay? So now what I'm going to do is I'm replacing this force of gravity by mg. And remember, while using this formula, we just write the values. So we don't worry about the direction of those. Directions are taken care by drawing this and figuring out the angle. So these are just the values, okay? So theta, depending on which way object is moving, theta could be 180 or 0 or some even 90, right? So value of angle could be different. So in this particular example I'm talking about, it is 180 degree. So this energy transfer that takes place because of the work done by gravitational force is the gravitational potential energy. And we denote gravitational potential energy by using this uppercase U. Remember, for kinetic energy, we use uppercase K for kinetic energy. Now, we use gravitational potential energy, to denote gravitational potential energy, we use uppercase U. And there are more than one kind of potential energies. So to be more specific about this gravitational potential energy, we put this subscript Z. Sometimes we may not, because we haven't talked about another kind of potential energy yet. So I think next class we'll talk about another potential energy called elastic potential energy. And you'll learn about yet another kind of potential energy called electric potential energy in physics 2. If you decide to take physics 2, that's where you learn, no matter whether you join my class or someone else's, that's where you learn elastic potential energy. Not the elastic, but the electric potential energy. Okay. So basically, that transfer of energy is the gravitational potential energy. And if we pay close attention, there is this displacement. We have this height over here, okay? So when we measure height, what happens is we measure from somewhere. So when we say, okay, what is my height? If I have to measure my height, what do? I stand on the floor and then I measure from floor to my head. Especially when I visit doctor's office, what they do, they make me stand in a place on the floor, and then they put a stick on top of my head, and then they read the reading over there. So that's my height. So the floor is reference point, what we like to call, okay? So I'm holding, I don't know if you can see my video, it's a kind of bit small, but if you pay attention, probably you can see it. So because we are sharing the screen, right? So video becomes small. So I'm holding this pen and you cannot see it, but down here there is a table, okay? And there is floor. So what's the height of this pen? For example, how high this pen is? If I ask that question, probably you will wonder, are you talking about from the top of table or from the floor, right? So where you measure the height from, that makes the difference in terms of what's the value of the height. So that's why we have to be specific about where we are measuring height from, okay? So choosing some point as a reference point makes it easier than choosing other points. So for example, if I'm trying to measure height, how far it is from some place. So for example, if I choose reference point as a ceiling over there, may not be that practical or helpful, but that does not mean I cannot choose reference point over there. I can, okay? So depending on situation, choosing reference point wisely makes solving problem bit easier, okay? And we'll talk about where to choose a reference point to solve problem. We'll talk about that soon. But for now, keep in mind wherever we choose a reference point, remember reference point is the point or the line from where we are measuring height from. So at that point, the height is 0. So since this equation has a height in it, when height is 0, the gravitational potential energy also becomes 0. So at that point, gravitational potential energy is 0. And if you go any higher than that, then what happens? Gravitational potential energy is now increasing. You go higher, gravitational potential energy increases. You come lower, gravitational potential energy decreases. So that's how it works, okay? So for example, let's say there is this point where I say, okay, if I choose floor as a reference point, and if the object is sitting on the floor, then initial position of the object gonna be 0. And when I lift this thing up, for example, just like we are lifting this bucket, what happens? Its final position gonna be at certain position. So we can say, okay, the final position is equal to height because initial position is 0. Because this height is basically displacement in y direction. That's what the height is. What is height? It is displacement in vertical direction. That's what the height is. So that means height is basically final position minus initial position, which is displacement, okay? And that change is also sometimes we may denote as a height. If initial position is 0, then in that case, final position and height, they are same. So basically, the gravitational potential energy depends on how the position is changing in vertical direction. Higher you go, we say, okay, gravitational potential energy is higher, and you come down, it's lower. So now let's use this angle 180 for this particular situation here. And then what happens here is that this is cosine 180 degree, so which is -1. So the work done by gravitational force is this. So there is this negative sign because of this angle, but if this angle is different, then there may not be this negative sign. So what we do is we just choose this portion here. So product of mass, this, the gravitational acceleration due to gravity, acceleration due to gravity or gravitational field strength, product of that times this change in position, which can also be sometimes written as a height, okay? So if you see it's written as a height, it is basically same thing. So this three thing, we define that as a change in gravitational potential energy, right? So U means potential energy. When you have subscript G, that means it's gravitational potential energy. When you have delta, that means change in gravitational potential energy. Why is change? Because it's coming from change in position. Okay. When position changes in vertical direction, gravitational potential energy changes. So that's what that equation is telling us. Okay. So now, so these are intermediate steps. So let's forget about them for now. So we have this important relationship between work done by gravitational force and change in gravitational potential energy. You see, they have opposite sign. So what it means is when one has a positive sign, another one has a negative sign. Okay. So for example, in this case, work done has a negative sign, right? Because the angle is 180 degree. In this case, work done has a negative sign, so the gravitational potential energy, change in gravitational potential energy is positive. So if something is going up, change in gravitational potential energy is positive. So that's what it means. So for example, here, we'll, so that equation is telling us that if we go higher, what happens? Gravitational potential energy becomes higher. So let's put some numbers here. Let's say over here it was 6, positive 6. And over here is positive 10. So what is it? Gravitational potential energy I'm talking about, okay? I'm writing the values, some random number, but what is important is when we go higher, the value is higher. So this 10 must be bigger than 6, okay? So now if you find change, what happens? So this is like an initial value. When you are going up, this is initial, this is final. So change in this case, being final minus initial, change is how much? Final is positive 10, and then negative sign, and there is positive 6. So that gives me positive 4. Right? So when we go higher, change in gravitational potential energy is positive. But when we went higher up, displacement up, gravitational force down means the work done was negative. See how the gravitational potential energy and the work done has opposite sign. Number is same, but the sign of the number is opposite. So that's what this equation is saying. So if we go other way around, for example, if you come down, for example, right, then what happens? This is 10, but now this becomes initial because we started from up and coming down here. Final is 6, for example, okay, positive 6. So now if I calculate same thing, in this case, what's going to happen? YF is now positive 6, and then yi is, of course, I need to remember there is negative sign in the formula, and this is positive 10. So that makes negative 4. See how when object comes down, change in gravitational potential energy is now change is negative. Change in gravitational potential energy is negative. So change in gravitational potential energy negative means work done is positive. How do I know that? Can I prove that? So when you are coming down, displacement is down, and force of gravity, of course, always down, right? So that means the angle between them is 0 degree. So cosine 0 degree is positive 1. So that means the work done going to be positive. See, the change in gravitational potential energy is negative because change in position becomes negative here, okay? But work done is positive. See, they have opposite sign. So that's what this equation is saying. And I'm emphasizing this so much with example because this is a very important concept. And even when you are doing this, let's say learning about the potential energy due to electric force, we call that electric potential energy. And this equation is true for that one as well. This is true for any kind of change in potential energy. Okay. And by the way, change in electric potential energy has a special name, our household name. We call that voltage. Okay. We call that voltage. That voltage thing you hear about, you talk about, that is actually electric potential energy. So in that case, charge is moving in electric field. So the work done by electric field when charge moves from one place to another place is called electric potential. That's the change in electric potential energy. And household name for that is voltage. And unit of that is volts. Okay. Uh, oh, electric potential energy has a unit actually joule, but the potential has a unit volt. So anyway, you learn about that more in physics too, but the idea of this is same. So let's keep that in mind. So what did we learn? The work done and change in gravitational potential energy, they have opposite sign. When one is positive, another one is negative. So if you know sign of one, you know the sign of another one. Okay, so that's what it means. So now let's write the formula, how we use that to write the potential energy. Remember, for kinetic energy, we wrote this as a formula. So now let's write the formula for potential energy. Okay, so this is change in gravitational potential energy. This is mg delta y, or mg times displacement in vertical direction, or mg times height, change in height. Okay, so this is change in gravitational potential energy. It is change. So what is gravitational potential energy? How do we write it? So I write gravitational potential energy as mg. See, here we have mg, and when we have this change in position, we have change in gravitational potential energy. That means when we simply write position, that is the gravitational potential energy at that point. Okay, so this is simply mgy, but sometimes you may also see it's written as a mgh. Okay, so position in vertical direction, you can also write in terms of h, that's fine, but I like to use y because we've been using position in vertical direction as a y, remember, and position in horizontal direction as a x. So I'm just sticking with that notation. So this is the gravitational potential energy, to be more specific. Okay, so if you have to write initial, then you can just stick that initial subscript in y, initial position. Okay, and do the same thing for final. So that's how we're going to be using gravitational potential energy in this class. Okay. Okay. So I think I covered all this. So now here is this question for you. Oh, I thought I started clicker, but looks like I did not. Okay, here it is. And this is 2, right? Yeah, today is Tuesday. Oh, sometimes I forget. So let me open this poll. So you have 1.5 minutes for this, okay? ball is going down. So what's the sign of the work done by gravitational force? And change in gravitational potential energy. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So mostly B, and C is also competing with B. So what's the difference? Positive versus negative. But both of them, they say, okay, they have opposite sign, right? If you choose this, say one positive, another negative. If this is negative, that's positive. So that part is correct for both of these. But is the work done by gravitational force when something coming down positive or negative? How do I figure that out? I need to draw FD diagram, right? F, force of gravity is down. And since this ball is coming down, displacement is also down. So that means the angle between them is 0 degree. The cosine 0 degree is positive 1. So that makes the work done by gravitational force, which is force of gravity times displacement times cosine theta, as a positive, because Fg, for example, is mg d cosine 0 degree. So that makes positive mgd. So work done by gravitational force is positive when something is coming down. And since we know the change in potential energy has an opposite sign, this is the correct answer. Okay, so B is correct answer in this case. Okay, so just by remembering that, you can do that. Or if you like, you can also calculate change in potential energy. Since it's coming down means height is decreasing. So yi, yf, and yi is larger than yf means change in y is negative. So that gives you what am I writing here? Mg delta y as a negative mg and that value, whatever. So let me just write negative here. So since it's coming down, change in height is, or change in position, final minus initial is negative, okay? So just like I said in the previous, slide, for example, if this is 10, it's coming down, means YF gonna have a smaller value, let's say 8. So final minus initial means 8 minus 10 is negative 2. So that's what I mean when I say change is negative when initial is larger than final, okay? So that's what it means, okay? So you can actually do the calculation, but if you remember that change in potential energy and work done has an opposite sign, you can answer this without doing this part, just by doing this one here, okay? Or you can just do one part here, this, and you don't have to do this to just answer this question. Okay, so that is about positive and negative. So how much is it then? So here is a question for you. So I just noticed there is a question on Zoom. Yi is 0, right? It is not, okay? It's coming down. So 0 would mean it is just sitting on the reference point. So it cannot go below that in this case, okay? So this is 10 versus 8. So that's why the yi is bigger than yf, okay? Okay, no need to apologize. Okay, so now here is question. It says work done by gravity during this journey. So what's happening here? It starts from here and it goes up. So that means it starts something like this and goes straight up and goes sideways. So for example, for the loop, I'm using this box I have next to me. Okay. Let's see if I can that. Oh. Okay, so it starts somewhere here, let's say, goes up and then sideways and then comes down, right? Something like that. That's what happening. So it's not moving along the horizontal direction, rather, it is moving vertical direction here and then sideways here once it goes on the top. So that is horizontal and then comes vertically down. So it goes half meter up, coming down 1 meter down, and then goes sideways. So starting point is this. So that means this is like a yi and this is like a yf. Okay. So with that said, I'll let you work on this. And you have 2.5 minutes to work on this and answer this question. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So we got A, B, and E mostly. There is D as well. So 10 joule versus 5 joules, and positive sign versus negative sign. So most confusion, since we got most between B and E, most confusion comes from the sign. Positive versus negative sign looks like, okay? So I'll show you two different ways of doing this, okay? Two different ways. One, direct and short, by just using this formula once. Work done by gravitational force is equal to force of gravity times displacement times cosine of angle between them, okay? So in this case, gravitational force is mg. Now what is displacement? See, initial position is here, final position is here. So from the definition of displacement, or delta y, it is yf minus yi. So basically, while using in this formula of work done, we don't have to worry about positive or negative sign. We just use the value. So this whole thing is 1 meter, and this is half meter, means this is just half meter, okay? So that means D gonna be just half meter. And cosine, what's the angle? So displacement is down. So the object went down here, D. And then force is also down because gravitational force is always down. So the angle between them is 0 degree, means the cosine. So I think I have cosine here. So let me write that down over here. Cosine 0 degree is positive 1. So that gives me 1 times 10 times 0.5 as a 5, and it's positive, and the unit of the work done is, of course, joule. So if I were to just write units as well, what's going to happen? Mass has a unit kilogram, G has a unit meter over second square, and then there is this unit meter over there. And then the cosine 0 is just a number, positive 1. And if I look at this, kilogram meter over second square is mass times acceleration, so that is Newton, and this is meter. So Newton meter is called joule. So anyway, we learn unit of work done or energy is joule. We talked about that last class, so you can just remember that if needed. So looks like B is correct answer in this case. So a lot of you chose E. So number-wise, that was correct, but the value. So in this case, this is saying work done, not the change in gravitational potential energy. If we are talking about change in gravitational potential energy, then this would have opposite sign. But the question was just to find work done, okay? And work done and change in gravitational potential energy, they have opposite sign. So probably that's what you thought here. So yes, even a small mistake like sign becomes huge mistake. So that's why I always encourage you to actually draw the F force and displacement and figure out the angle between them. That gives you the sign of the work done. Okay. So now we did that. But let's do slightly differently. So you may be thinking, okay, it started going up. Why we are not calculating that? So short answer is work done is force times displacement times the cosine of angle between them. So it's the displacement, and displacement simply can be drawn starting from tip of the initial, from the initial to final. That's how we draw the displacement vector. That's what we have learned, okay? So displacement here is simple. It doesn't matter what happened in between, okay? But let's say if we were to keep track of all of these, will we get the same answer? Let's try that, okay? So for that, we need to find work done while this is going up. Let's say that is W1, and work done while it's going sideways on the left. Let's say that is W2, and this is W3, this is W4, okay? So let's calculate all of these individually and then add them together. That way we can tell what the total is, okay? We can do that one as well. So let's look at W1 first, okay? So W1 is mg times d, displacement, and then cosine of angle between them. So in this case, what is angle? The force is down here when it is moving. Force being gravitational force always down, but this time it's moving up. So D is up. So that means it is 180 degree. Theta is 180 degree. So that makes it M 1 kilogram, G 10, and then D is half because it went up there from here. So this is half meter, 0.5. And then cosine 180 is negative 1. So that's what gives you negative sign. So now I'm getting negative 5 joules when it goes up there. Okay. So that is for this one only. Now for W2. Let's calculate W2. Again, force is mg. Displacement is, let's say, d. And cosine of angle between them. So to find the angle, what do? We draw FD diagram. So in this case, force being gravitational force vertically down, but the displacement is sideways. So the angle between them, theta, in this case is 90 degree. So that means for this portion, what happens? Cosine 90 is 0. So that makes this, no matter what the value of mg is, what the value of d is, once theta is 90, work done is 0. So W2 is 0. Okay? So now, if we look at here, W4 is also 0. So see, the displacement is this way and force is this way. So the angle between them is 90 degree, means work done is 0. So now let's find the W3. While this thing is coming down. So again, we are using the same formula, but this time, what is theta? See, D is down, it's coming down, and force is also down, of course. It's a gravitational force. So theta is 0 degree in this case. So that makes this 1 times 10 times D is also 1 in this case, and cosine 0 degree, which is positive 1. Okay. So that makes positive 10 joule. So what we have is one negative 5 joule, another positive 10 joule, and other two zeros. So the total work or net work in this case is positive 5 joule. Why? Because negative 5 and positive 10 is positive 5, right? So that's why it is positive 5 joule. So why did I do it this two different ways? One, to show you you can do it. Another one is that work done by gravitational force is path independent. It does not depend on path, which path it goes. So even if it had gone all the way up and gone down all the way and had arrived here, making initial and final position same, then the result would have been same. So it's path independent. Go this way and come back here, same result. Okay, so it's path independent. Easy to see. It simply depends on displacement, and no matter which path you take, displacement is just that. Displacement vector, remember, we draw from initial position to final position, right? So that's the displacement vector we draw. So that's what I'm, saying same thing here in this slide. In this slide. Oh, there is slide as well. Okay, so there is this path, there is that path. So in both cases, what happens? Since the change in gravitational potential energy or the work done simply depends on this change in vertical position, change in vertical position for both of these paths are same. So that's your initial and your final is there. So initial and final, they are same no matter which path it is taking, okay? And height is same. So delta y is same for both path, okay? So let's suppose there is a mountain like that, and something like this. Base of the mountain is same, let's say, okay? So my friend who is kind of rock climber and so on tries to take shortest path and climbs from this way. I am not being a rock climber, try to avoid steep height. So I go this way, but initial position in vertical direction and final position in vertical direction, they are same for both me and my friend. So that means change in height is same. So the work done by the gravitational force on me and my friend, it's the same as long as we have same mass. But remember, work done also depends on mass. So if we have different masses, probably my friend being rock climber may have a smaller mass than my chubby mass, okay, and bit lazy person, okay. So if the mass were same, this, see, the change in position is same for both of us. So that gives us same change in gravitational potential energy, okay? So change in height is same for both path. So whether I am climbing down this path or that path, change in gravitational potential energy, my change in gravitational potential energy is same, okay? So that is kind of interesting. So it is path independent. When work done by a force becomes path independent, that kind of force is called conservative force, okay? So gravitational force is such example, one such example of conservative force. But all the forces that we can define potential energies, they have this property. They are conservative. For example, I said, or I talked a little bit earlier about electric potential energy. See the electric potential energy? So that means it is the work done by the electric force. So electric force is also conservative force. Other way around, we can define potential energy for each of the conservative force. So it seems like all forces are conservative. Do I have example of non-conservative force, right? So for example, if I have a friction force, what happens is, let's say, yes, so if I have a conservative force like gravitational force, when something comes back to the same point, for example, going something like that in a loop, so initial and final position, same. So in that case, change in height is 0. So that makes this gravitational potential energy, change in gravitational potential energy 0, or gravitational work done by gravitational force is 0. But let's say if I was talking about work done by friction force, what's going to happen? So to make things bit simpler, let's make a loop like this rather than circular loop. So let's say if we start dragging something this way, so displacement is that way, so friction force acts opposite direction. So angle between them is 180 degree. So work done gonna be negative. Okay, work done gonna be negative. Now, when I'm dragging this on this side, what happens? Displacement is up. The force is friction force, being this being friction force, it's opposite to the motion. So angle is still 180 degree. Okay. Same thing goes here. When I'm dragging here, what happens? Friction force is opposite of the motion, so the angle is 180 degree. So every time angle is 180 degree, work done gonna be negative. So while going up, negative, while going right, negative, while going left, negative. And you guessed it, while coming down, it's negative as well, work done by friction force. Because displacement down, friction force up, means the angle is 180 degree in that part of the loop as well. So work done is, work done by what? Friction force is negative all the time. So if I were to add all of them, just by adding negative, 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 you will never get 0. So work done in a loop is not 0, means it is not a conservative force. It is non-conservative force. Friction force is an example of non-conservative force. Okay. So now with the conservative force, now let's move towards talking about conservation of energy. Before we do that, let's talk a little bit about what is positive and negative work means, okay? So when we say positive work indicates transfer of energy to the object. So if a force is doing positive work, it is transferring energy to the object. So for example, the chair is there. If I give a push to a chair, so chair wasn't moving or moving slow, and I give a push, I did work. And because of that, what happened? So I pushed in the direction of motion, so the work done is positive. So because of that, kinetic energy of the chair increased. But let's say chair was already moving, it was sliding. And then what I did was I pushed in the opposite direction. So that means I did negative work. So I'm applying force opposite to the motion. So something is, coming towards sliding, coming towards you sliding, and you push it away. What happens? Object slows down, means its kinetic energy becomes smaller. So that kinetic energy, the energy from this object, that chair that was already moving faster, now got transferred to the object that's applying force on, okay? So that's what the negative work done means. So negative work indicates transfer of energy from the object, not to the object. So object here is the object at which work is being done. Okay, so that's what the object is. So for example, if you are pushing chair, chair is example of that object. Okay, so now, so energy transfer, that's what the energy transfer means. So for example, here, this person is lifting the weight. So weight was on, weight was on the ground. And then this person picks the weight up, lifts the weight up. So that means now it has a higher height. So portion applied force upward and displacement is upward. So work done is positive. So that work done gets transferred to the object. So that's why object is higher now. So it has now, we say, higher gravitational potential energy. When you lift something up at higher height, it has now higher gravitational potential energy. Okay. So the work done by this athlete or the player got transferred to the potential energy of that weight. Okay, so that's what's happening here. So now we see, I don't know if you have, what's this kind of game where people jump and try to, like let's say, jump high as possible, this high jump, right? When they are playing this game, they don't just jump right from there and try to get there. Okay. They first run. So when they are running, they have now kinetic energy. And then when they jump, that kinetic energy gets transferred to the potential energy. So kinetic energy is transferring into potential energy. So what that means, one kind of energy can transfer into another kind of energy. So one form of energy transfer to another form. Kinetic energy can transfer to potential energy. If I drop something here, what happens? It has a higher potential energy at the top, at higher height. Once it starts moving, its speed increases, means its kinetic energy is now increasing. So potential energy is decreasing because height is decreasing. At the same time, kinetic energy is increasing. So energy can transfer from one form to another form as well. Okay. So in that case, drop of the ball, we saw gravitational force is doing the work. Okay. So the energy, all kinds of energy, they can transfer from one form to another form if we can use, a suitable method. So for example, here we said, okay, this person transferred the energy to the weight over there, this athlete. Okay. Where did the energy come from? Okay. Like where did this player get the energy from? Where did the energy come from? So you have energy, right? You can lift things, you can transfer energy, but where is that energy coming from? You may say, okay, it's coming from me, but you cannot just create energy. Where is that energy coming from? Where does that energy come from, folks? So we have now energy, we can lift weight. Yeah, some of we may able to lift more than the other, but where does that energy come from? From body movement. Okay, yes, body movement. So muscle, they are stretching, right? But where that energy come from? Okay, so there is this response that says from food we eat. Okay, yes. So food has energy, remember? They say, okay, count calories, don't eat much more than you spend, something like that, right? So calorie is another unit of energy. Okay, so basically it is energy. All food has energy. So we eat energy. I mean, we eat food means we are, so that food goes through chemical reaction in our body and becomes energy, right? And where did the energy on the food come from? Where did the food get the energy from? Ooh, Okay, so there is great response there. Plant from the sun, animals from their food. Okay, animals like us, we eat food. So yes, so food gets energy from sun, and we can have animal food, of course. And so they get energy from the plant. Okay, so eventually energy is coming from the sun. Ooh. See how the energy is just transferring from one place to another place. See, there is no generation of energy, actually, no creation of energy. Energy can only transfer from one form to another form, but we cannot just create energy from nothing. Okay? So it has to come from somewhere. That idea, that fact is called conservation of energy. Okay? That fact is called conservation of energy. So here is an example of energy you supply on the string. You pull the string on the uh, in this bow, and then what happens? Once you let it go, that energy gets transferred to the kinetic energy of this arrow. Okay. So all the energy we have here on the earth, that comes from the sun, basically. Almost all of them. Okay. And there can be energy from eventual source is basically this nuclear reaction. Okay. So we can also generate energy from nuclear reactors where mass gets converted into energy. Mass gets converted into energy. Other than that, all the energy we have, petroleum and so on, all those are the result of the energy coming from the sun. Okay. No sun, no energy on the earth, and everything gonna be gone. So we cannot create energy. We just transfer from one form to another form, and that is called conservation of energy. So seems like it's good time to take break. So we'll take break and then talk about these conservation of energy, and we'll learn how to use conservation of energy to solve problem. That is the most important part. Okay. So I'll see you in 5 minutes. Okay, folks, so welcome back. So before break, we learned about gravitational potential energy, and we also talked about how one form of energy gets converted into another form, okay? So yes, we can have transfer between kinetic and potential energy, but we cannot create energy out of nothing. So this is called conservation of energy, okay? So mathematically, we can write that statement as something like total final energy is equal to total initial energy. In symbols, we can write something like this. Okay. So total energy means kinetic energy, potential energy, and there can be other form of energies. For example, thermal energy. We'll talk more about thermal energy. Usually thermal energy arises when friction does the work, right? When gravitational force does the work, we learn that gravitational potential energy arises. Similarly, when friction does the work, thermal energy or heat energy arises. So that's why when we rub our hand, what happens? It gets warmer. That's the thermal energy. Okay. So we'll talk a little bit more about work done by friction and how to use that in the equation a little later. But for now, let's just focus on these two kinds of energies, kinetic energy and gravitational potential energy. The sum of kinetic and potential energy, kinetic energy plus potential energy, the sum kinetic and potential is called mechanical energy in short. So mechanical energy is collective name of both of them. So when we say mechanical energy, we are referring to both kinetic and potential energy. Okay. So if we can neglect other form of energy, or the energy in the process of energy transfer, let's say another form of energy are not being generated, not being transferred, then we can just talk in terms of kinetic and potential, and that's what we are doing here when that's the case. So this is a special case where other form of energy does not exist. So in that case, total energy will be simply kinetic and potential. So sum of them gonna be equal. So this is kind of a little bit expanded form of that. And knowing that kinetic energy can be written as half mv square and potential energy can be written as mgy, we can expand this. So for example, kinetic energy half mv square, but this being final, we need to stick final subscript on the speed. And same thing, potential energy is mgy, but why has this final subscript? Because we're talking about final gravitational potential energy. So while solving problem, eventually we have to write in this form. I think in formula sheet, I have included this equation as well. But even if it is not there, by knowing that total energy before and after are equal, you should be able to expand this and then write this. Once you know kinetic energy is written something like that, and potential energy is like that. And those appears in the equation sheet as well. Okay. So now with that, with this knowledge, we should be able to answer a question like this. Okay. So to actually answer this question, we may have to actually do a little math using that formula or conservation of energy. But let's say you have to make educated guess, okay, rather than going through all those formula. Let's say you want to make a guess and answer this question, okay? And what kind of guess? The educated guess, that way what we have learned, okay? So what would you choose? So I haven't shown you how to solve this kind of problem yet. So don't worry about being right or wrong. Try your best and poll on this question, and you have a minute to respond to this. 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So mostly yes. Okay, so it's ice, right? It's gonna just keep slipping and gonna go to the top no matter how high it is. So that's one way of thinking. Or maybe it cannot. Okay. And or tell, okay, it's hard to tell. So here I'm gonna just tell you the correct answer because I remember the answer, but I'll show you how to do it in details a little later, okay? But before I solve this problem, I like to talk in general how to solve any such problem. See, isn't that interesting? You learn this method and you can use this method to solve any such problem using conservation of energy. So for that, what do we need to do? So conservation of energy has this kind of equation. See, it has initial and final, right? Initial and final. So that means we need to mark or label initial or final after we read the problem. So that's why I have written this in the note that I have provided you folks, right? These steps here, mark initial and final, initial position and final position. So at initial position, you need to write what is actually value of initial position or final position. But before you can write the actual value of initial and final position, actually you need a reference position because that's where we are measuring positions from. So if we don't know where we are measuring from, we cannot tell what position is, okay? So you need to label these three things, okay? So often I see student skips this. That is not the way to go. So I'll be posting another worksheet soon. So that worksheet will have this problem where you're going to be using this conservation of energy to solve problem. So you're going to be showing all these details in the worksheet, okay, to earn full points and learn how to do it. And that's what I'm saying. So it's not that difficult. So for example, in this case, what do you see? This person, this guy, this player is Tiger Woods. I think one of the best athlete in golf, I guess. Uh, so dropping this ball, okay? So this ball is being dropped from here. So that's why we label that as the initial. And it arrives to the ground. So we can say, okay, the ground is final position. And now how do I choose a reference? Often measuring height from the ground is easy. So that's why it's a good idea to choose that as a reference point. Okay. So solving problem becomes easier if we could choose either initial position or final position as also the reference, okay? Either one of those as a reference. So problem becomes a little bit simpler. But remember, we are free to choose anywhere we like, but choosing wisely makes problem solving bit easier, okay? So that's why I am suggesting you choose a reference point either at initial or the final point whenever possible, okay? But if that's not obvious, then you may have to find another suitable example or position, okay? So we'll look at the example of choosing at either initial or final, just like we are doing here, and also choosing somewhere else, okay? So we'll look at the examples. So these are the process you go through, and then you write this, okay? This is coming from this main equation. Total final is equal to total initial. And in this case, the energy involved are just the kinetic and potential. There is no friction involved when ball is falling, right? And by the way, to solve this problem, you can also use kinematic equation, by the way, okay? You can also use kinematics equation here. Ball drop, falling object, free fall, right? So you can also use kinematic equation. You can do that. So now, since you know several different ways of solving a problem, you can solve it using either one of those, wherever you can. But here we are trying to learn how to use conservation of energy. So why that is important? Because there are going to be some problem where you cannot use either kinematics or dynamics to solve the problem, okay? And one such example is the example I was just, talking about. Here, what happens? So this problem you cannot solve by using kinematics. Why? Because when it's moving something like this, see, it is moving something like that. So the acceleration is changing. So whenever acceleration is changing, you cannot use kinematic equation. Kinematic equations are only for the situation when the acceleration is constant. If acceleration is changing, then you cannot use it. So you can use kinematics for this portion because slope is constant. So is the acceleration, but here slope is changing. So the acceleration is changing means you cannot use kinematic equation to solve problem going from here to there, okay? Now dynamics, same thing, since the acceleration is changing, in dynamics, remember we write the equation something like this, mass times acceleration. So one equation for one acceleration. So since the acceleration is changing several places, you may have to write several equations if you plan to use this to solve this problem. And over here, there is velocity given, and in dynamics, there is no velocity in the equation. Maybe not a good idea to use that. So that's where this conservation of energy comes in. So for that, in conservation of energy, what happens? Only the 2 points matter, initial and final points. What happens in between does not matter. So because of that, solving problem in many cases becomes a lot easier using conservation of energy than kinematics or dynamics. So now let's learn how to use the idea we just talked about here for this problem. And by the way, this portion is from another problems that I have done in the note. But no matter which problem I have done, for each problem I have labeled initial, final, reference, initial, final, reference. You see, those labels are always there. And reference rather than a point is going to be a line, okay? So now here, let's choose initial and final. So initial is easy. When we spot it, it is moving, right there. So we can say, okay, that is the initial point. That's the initial position point of the object, right? Final. So now the question is, will it reach here or not? So that was the question, right? Will it make to this height? So how do we find that? So we need to find final position and compare with this height. If final position is larger than 1 meter, then of course it makes it. But if final position is less than 1 meter, then it's not going to make it. Okay. So where the final position? We don't know. Okay. If it does not make, it's going to be somewhere there, right? But if it makes it, it may keep going and it may go even higher. We don't know, right? But we need a final position. So let's choose a final position saying, okay, that's where that is. Could be anywhere. That point could be anywhere, okay? I'm just putting it there. Now, we have final here. And let's say reference, okay? We can measure from this point here. So this is going to be reference line. So I label the initial, final, and reference. So now next step is to write what are the values of these, okay? So what is the initial speed? See, initial speed is given as a v, which happens to be 4 meters per second. Sometimes remember this number may not be given, okay? But here this number is given. And what is initial position then? Can you tell what the initial position is? Initial vertical position of this object here. So initial is right there at the reference line. So it's like saying object is on the floor. What's the height of the object when it's sitting on the floor? That is 0. Yes. Okay. Now, final position, that's what we like to know. We don't know where it is. Do we know about final speed? So final position is the maximum height it can go. Remember, this position I am talking about, these are vertical positions we're talking about. So it's the maximum height. When object is at maximum height, what happens to the speed? That's when it stops, right? So that's why it is maximum. If it keeps going without stopping, then that's not going to be maximum. It's going to be some in between. So we can say, okay, the final speed is 0. Okay. So now after that, we can now write the equation. Okay. So I'm going to be writing here. So in this case, see when you have positions and the speeds are given, no acceleration is there. So most likely you want to use conservation of energy idea. Okay. When do you use conservation of energy idea? When you have speed and positions. Okay. Speed and positions without any acceleration. Or if the acceleration is changing, in that case, you want to use, you want to definitely use conservation of energy. So conservation of energy, total final energy is total initial energy, or we can write this as a final kinetic energy plus final potential energy is equal to initial kinetic energy plus initial potential energy. See how I'm repeating same thing, right? Since we want to write in terms of these, I want to expand this half mvf squared. And by the way, this kind of looks like a B. So this is U actually. So potential energy is mgy. So for the final, I put the subscript that. So that's kinetic, that's potential. So that's the left-hand side. And to right-hand side is the same thing, kinetic plus potential. Only difference is now initial. So that means you replace that F subscript by I. So you just copy this, but replace F by I. Copy the left-hand side, but replace F by I. So yes, looks like a lot of terms and maybe, sound or look difficult, but it's not that bad. Okay. You're just copying the terms. Okay. So now once you have that, whenever I have something 0, I like to get rid of that term right away. So yi is 0 means this term gonna be 0. Final velocity 0 means this term gonna be 0. And what are we looking for? Final position. This we are looking for. So let's keep that right there. And on the left hand side, we are left with half m bi squared. And you see the mass cancel, so we don't need mass to answer this question. Okay. So now I'm solving for yf because that's what we are looking for. So I have on the side vi squared, and bi is basically v, so I'll just write v squared. Remember, vi is just v, or you can write 4 square, but I like to first solve in terms of variable. And 2 is there. Now g comes from here. Since it is multiplying yf, it's going to come and divide. So that's going to be that. So that makes 4 square over 2 times 9.8. So this is 16 divided by 19.6. I did not write the units, but the eventual units should be meters here. So you see this is yf is less than 1 meter, or less than the given height, less than the given height. So that means it does not make here. So it's going to make somewhere there and going to come down, okay? It's going to go up and then come back down. It's not going to reach to that height, okay? Okay, so that's the answer of this question, but more importantly, this is how we solve problem using conservation of energy. So this is one most important skill, okay? So how do you use kinematics to solve problem? We learned that. How do you use dynamics to solve problem or Newton's laws to solve problem? We learned that. Now we just learn how to use conservation of energy to solve problem. So now we have most of these skills except one conservation law, which is conservation of momentum. We'll learn about that next week. Then basic physics is done, folks. Remaining gonna be just application of those in different situations. That's it. So here is a question for you. So over here, what was happening? Object was sliding up in something like this kind of slide. Now, let's say something is rolling downhill in similar shape there. But there are these, see here, the ball can start from either here or here or here or here, right? And we are asked to find what's the speed when it exits, right? Speed here. Seems like there is a hand up. Yes, your microphone is off. Okay.
So the thing you used to poll is kind of blocking the question, part of like the question you wanted us to
Oh,
answer.
oh,
The
clicker is.
collapse toolbar
Oh, I
is kind
see.
of blocking.
Okay. Yeah. Thank you for letting me know. Okay. So that is our final position. So ball can roll on this one or that one or that one or the straight one. That's what we're calling ball number one, right? And ball two could be any one of remaining three, okay? Rolling from any one of those three. So this is like fairly straight. You can see that, all right? So now the question is, which ball gonna leave with highest speed? Which will have the largest speed? So if we think about it, this problem and this problem, they are same. Here the object was climbing uphill. Here object is climbing downhill. Other than that, same problem, okay? So you can just think in terms of one ball, how the motion of one ball, how do you find the speed of one ball? And then once you have that, you can use the same idea for each of those ball and compare, okay? So with that said, I'll let you work on this. And you have 2.5 minutes to answer this question. Try your best. You should be able to answer this question correctly from what we learned in the previous slide. 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got. So mostly we got C as the correct answer. Is it correct answer? Turns out that is the correct answer. So once we label, so it is like situation where it goes something like that. It's like our regular slide thingy, right? So top is initial, bottom is final, and right there is a reference, right? So initial position is whatever the height of this one is, okay, whatever this height is, that's the initial position. Final position is 0 because we are choosing reference right at the bottom. And initial speed 0 for all of them. It says it starts from the rest. They are released from rest. Okay. And we want to find final speed. So for each ball, all of these are same. So that means final speed should be same. Even if the mass of the ball are not same, because mass cancels, mass independent, right? Mass cancels when we write the formula. So for example, if I were to use the same idea we did here and write this equation here, how would that gonna look like for this one here? Let's see. So final kinetic energy plus final potential energy must be equal to initial kinetic energy plus initial potential energy. And just like we wrote, YF and VI are 0 in this case. VI is 0. YF is 0. And we are asked to find just VF. So what are we left with? So now mass cancels. You see that? So VF is 2GY. YI is basically H. Let's plug in H for that. Same for all of them. So since this height is same, they are released from same height, and the final position is also same, the final speed is gonna be same. G is same for all of them. In this case, in this example, H is also same for all of them. So that means final speed should be same. So let's throw some balls here like this. Now, what do you think? And for this, you have a 1.5 minute. 30 more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. So here, all of these balls starts from the same place. So that means initial position for all of them gonna be same. Let's say that is that whatever the height it is, okay? And initial speed is same for all of them. It says same speed. And in kinetic energy, it's the speed that goes in there, not the velocity. Direction does not matter. Okay. So VF, we want to know what is YF. So see, all of them are reaching to the ground, and we are choosing ground as a reference. So final position going to be 0. Okay. So with what speed they reach to the ground. So that's what we want to find, right? So using the same idea that we learned, see, initial is same for all of them. So final position is same. So that means final speed also should be same. We can tell that. Okay. So yeah, just like many of you thought that, but red, some of you thinking, okay, it's coming down from highest height. What happens is, since all of them are thrown with the same speed, this ball slows down and then starts speeding up. By the time it arrives here, it has a speed same as the speed it had initially. Okay, so it is like as if it was thrown with the same speed. So solving this problem using projectile motion, these are like example of projectiles, but using projectile motion kinematics is a lot difficult here. But using this idea of conservation of energy is a lot easier. See how some problem becomes a lot easier using the conservation of energy. So if I were to write equations just like in previous slide, so I can do this. So YF is 0, so that means this is going to be 0. Other than that, none of those are zeros, but mass cancels in this case as well. Oh, I said mass cancels, but forget to cancel it. Okay. So this equation is very similar to the equation we saw here. See, it had 2gh. If the initial velocity was 0 in this case, if this was 0, this would be just 2gh. But since that is not 0, this is not. So see, the v is same for all of them. H is same for all of them. So that's why the final speed is going to be also same. So mathematically, we can prove it using conservation of energy idea. Okay. And here is another question where it is convenient to choose a reference over here, but the initial is over here and final is there. So this is one example where a reference is not either at initial or final. Okay. But yes, of course, you can also choose reference over there. You can do that, we can do that, but let's look at from here because looks like all these heights are given from this point. So it is good idea to choose reference over there. So initial final reference, so that means initial position is 0, initial speed is, it rolls down on the track, so it starts from, oh, initial height is not 0, my bad, it's 40 meters. Initial speed is 0. Final speed we want to know, and final position is 20 meters, right? So now you can use the same equation. See, when you write several times, this equation sticks in your head. So in this case, BI is 0, means this term is 0. So you are solving for BF, and mass cancels here as well. So it's going to be half BF squared is M, or let's get rid of mass, GYI minus GYF. I'm moving this term on this side here, okay? So BF square is 2 times GYI. Let's factor G out as well. So BF gonna be 2GYI minus YF under the square root. So same idea. And there is another example over there where this is kind of carved thingy, right? And you see, same idea is being used. Probably you are copying this one here. I moved it quick just to show you. So in all cases, you use the same idea. So learn properly how to solve at least a problem, okay, without looking anything with all these examples. And that will be a good starting point, and then start solving other problems, okay? So I had a plan of going through a couple of more slides, but looks like we don't have time. So I'll let you go. So if you have quick question, stay behind and ask me, or else I'll see you next class.